My name is Carine TEAV, and I'm working at the French Atomic Energy and Alternative Energies Commissions in France on improvement of active layers homogeneity for the membrane electrode assembly for proton exchange membrane fuel cell, and especially on the impact of the inequality formulation. So just to begin, an overview of what is a proton exchange membrane fuel cell. So we are working on that because due to an environmental context, in the aim to reduce pollutions in transport fields especially, and so we are developing high performance electric cars to replace classical cars of today. So how it works? It's a redox reactions which convert chemical to electric energy thanks to H2 and O2. And it consists of membrane electrode assembly, so the core of the fuel cell, and bipolar plates, which permits to input active gas. My work is to work on the improvements of performance and durability of fuel cells by working on the MES quality and more specifically on inks formulations for active layers. Where there is a reactions. So I will compare between homogeneous and heterogeneous active layers to compare it and if there is an impact on the fuel cell performance. So I will work on two axes, the process of ink dispersions and the order of components introductions in the ink formulation for active layers. So the idea is to find the best way to formulate and the best dispersion process to obtain homogeneous active layers with ink particle size below 1 micrometer. And then I will also study the viscosity and the stability of ink, and then check the impact of defects and agglomerates on the fuel cell performance. So about experimentals, I tried 3 methods of dispersion: mechanical dispersions, which is also our process of reference, high-sharing mixing, and also planetary mixers with 2 different ratios. So one which is 0.4 and then 0.9. Concerning the order of introduction of components, we have tested 6 formulations, and the formulation 6 is our reference formulation. About method of characterizations, to determine the particle size of our ink, we used green gauge and an electroacoustic probe. And then for the viscosity and all the rheological parameters, I used a rheometer. After being coated, so we can, I observed the structure of active layers thanks to SEM observation. And then after that, I put it in a fuel cell to test it in performance with different conditions. So I obtained polarization curves, which correspond to voltage in function of current density, and then we can compare the performance between active layers. About result now. So we have tested the 6 formulations for 1 process of dispersions, and based on the green gauge characterizations, I have selected the best 3 formulations with a very low particle size, so 1, 4, and 6, 6 which is our reference formulation, and to do a more complete characterizations after that. Then based on the 3 formulations, I determined the particle size in EAP for the 4 processes of dispersions and also the viscosity associated. So first trends, for the formulation 6, we obtained smaller particle size for planetary mixers, and for the high-sharing mixing, rotor and stator, I call that, compared to our process of reference that we can now eliminate. Then for planetary mixer, we have a better particle size, whatever the formulations. So it's quite a good process of dispersions, whatever formulations. And finally, a link could be made between viscosity and size of particles As we can see for the formulation 4, we have very low particle size at the left graph, and then the viscosity associated is very higher than the others. So this link has also been characterized with rheological parameters. So liquid inks which possess viscosity below 1 Pascal second will tend to destabilize rapidly, so very quickly, because it's very liquid, and so it will tend to agglomerate. So ink stability for active layers was measured by amplitude oscillations for 2 formulations, 1 and 4, one with a very low viscosity and the formulation 4 with a higher viscosity to compare it. First thing that we can see, is that whatever formulation and whatever process our ink behave like a viscoelastic solid ink, because the elastic component is higher than the viscous component, And for the formulation 4, we can notice that the elastic modulus is very higher than the other one, and have also longer plates, and which shows that the structure is maintained and the ink is very stable in the time. So it's quite a good relations. The phase angle corresponds to the grain curve, and when it's very closer to 0, it means that the ink will be very stable. So it confirms the fact that the elastic modulus is shows the stability of ink. So for us, the formulation 4 will be more stable thanks to its high viscosity. Concerning the active layers characterizations, the 4 processes was compared for same formulations, and the planetary mixers seems to be the best with better deposit and compared to the others, which present a lot of cracks and agglomerates. Concerning the comparison of the formulation 4 and 6 seems to be also more homogeneous, contrary to the formulation 1. But for our printing application, we need a high viscosity. So the formulation 4 will be more suitable to our application. And to finish, we have also carried out performance tests to see the impact of defect on fuel cell performance. So one MEA was with a lot of defects, and the other one was no defect and very homogeneous. It was carried out with different conditions, relative humidity conditions. And so I have measured the polarization curves. In the green, you can have the MEA with no defect, and in red, this one with defect. So for high percentage of relative humidity, it's quietly the same with similar performances. But if we decrease in relative humidity, we can see that there is a better performance for MEA without defect. So there is a real impact of the microstructure on fuel cell performance. So to conclude, in this study, I have studied two axes, the order of components introductions and the process of dispersions. So concerning the first one, it plays on rheological parameters, viscosity and elastic and viscous components on stability of ink. And process of dispersion has played on ink particle size. But we have also seen that viscosity and particle size are linked, because for a higher viscosity, we can have a very low particle size. And also stability of ink is also linked to ink particle size. The ink particle size will influence on the homogeneous of the active layer, which will itself play on fuel cell performance. To conclude, for us, for our application, formulation 4 present a high viscosity, is more stable, and will be more suitable to our printing process. And the planetary mixers with a high ratio of 0.9 could also be more suitable to our process. And just to a perspective, to go further in the study, I can make a single cell test performance and electrochemical characterizations of each formulation, so the three formulations I have tested, and also processes of dispersions. So, thank you for your attention.
Thank you for your presentation. So many parameters. Thank you very much. Thank you very much.
You're welcome.
Thank you.